In this section, we'll discuss Euler's equations for rotational dynamics. Euler's equations are the equivalent to Newton's dynamical equations, but for a rotating system. So in other words, these equations tell you, given a torque exerted on a rotating system, how that rotating system will respond to the torque. The first thing to keep in mind when we're thinking about rotational dynamics and applying the Euler equations for rotational dynamics is that we often refer the dynamics to two different coordinate systems. One system is called the space or lab frame. That's the inertial coordinate system. And often in that coordinate system, it's very easy to express the torques that are applied to the rotating body, but not so easy to describe how the angular momentum vector itself changes with time. The other frame that we're going to be dealing with for these dynamical equations is what's called the body frame. And that's shown here. Usually the body frame that we're interested in is the three orthogonal principal axes for our rotating system, E1, E2, and E3 hat. Now it's very important to keep in mind that because these principal axes are referred to the body, they're essentially painted onto the rotating object, and that means as the object is rotating, these coordinate basis vectors themselves will rotate. And so that means in order to do the dynamical analysis properly, we're going to have to cast the time derivative of all of our vectors in a non-inertial frame. So that will simplify often the response of the angular momentum, but it makes the expression for the torques quite complicated in a lot of cases. But very often when we apply Euler's equations, we'll be interested in the case where there's no torque anyway, and so we won't have to worry about what the expression for the torques are in either the rotating or the space frame. So in order to calculate the angular momentum vector, remember we apply the moment of inertia tensor to the rotation vector. The moment of inertia tensor in the principal axis is in the principal coordinate system is diagonal, so everything else here is 0. We apply that to the rotation vector as written in the body frame, and so our angular momentum vector is just this vector, lambda 1, omega 1, lambda 2, omega 2, and then lambda 3, omega 3. And this is the advantage of using the body frame, in other words, in using the principal axes, because the angular momentum vector is quite simple, and the angular velocities about the three principal axes are uncoupled from one another. In the inertial or space frame, the time derivative of the angular momentum vector is of course just whatever the applied torques are. But we're very often going to be interested in how the angular momentum vector itself appears to change in the body frame. And so recall that we have a way of expressing, relating the time derivatives of two different vectors, one as measured in an inertial non-rotating frame, and then the other one as measured in the rotating frame. You go back to a few sections ago, and basically you'll find that we have this relationship. So the time derivative of the angular momentum vector, as seen in the space frame, is equal to whatever the time derivative of the angular momentum vector is as seen in the body frame, which remember the body frame itself is rotating, plus whatever the angular velocity vector is. And remember, that term is just the applied torques, and therefore the time derivative of the angular momentum vector as seen in the body frame is just equal to the applied torques minus the expression having to do with transformation of the rotating due to the rotation of the frame. Okay, so there's two terms here. There's whatever the applied torques are, and then the non-inertial term having to do with the fact that the frame is rotating. And so now we can resolve this equation into the three components along the E1, E2, and E3 principal axes for our system. And each of those equations, those represent the Euler equation. So let's write those down. Okay, so the first thing we need to do in order to write down those different terms is to calculate the non-inertial contribution. So we need to take the cross product of the rotation vector with the angular momentum vector. Now keep in mind, both of these vectors, both of these can change with time, as seen in the body frame. The angular momentum vector can appear to change with time in the rotating frame either because there's an applied torque or because of the non-inertial term here that we're working out. And the angular velocity vector can also change with time. So keep that in mind. None of these vectors are necessarily a constant. Okay, so we take this cross product. What are we going to get? Well, I'll skip writing down this part live, and I'll just write down the answer here. Okay, so the cross product works out to be this right here. So we see we get the first term here that involves the moments of inertia about the E3 and E2 axes. But then we see we've got omega 2 times omega 3, omega 2 times omega 3. And we see something similar down here. Here's the third principal moment, first principal moment, but then we have this combination omega 1, omega 3, omega 1, omega 3, same thing with the bottom. And so this all works out to be a vector that looks like this. So we get lambda 3 minus lambda 2, and then the product of the two omegas, and so on. So what we end up getting is differences between the different moments of inertia here times the product of two of the angular velocity components. Okay, to work out Euler's equations, we also need to think about what the time derivative of the angular momentum vector is as seen in the body frame. So that's the time derivative evaluated in the body frame of this vector here. Now, if we were not in the body frame, the time derivatives of the moments of inertia themselves, those might not be zero. Because as the body rotates, it may reorient as compared to the x, y, and z fixed coordinate axes as seen in the space frame. And so if the body were reorienting, that means that the moments of inertia along the x, y, and z axes, those moments of inertia would change with time. And so this is a tremendous advantage that we get in using the body frame. In the body frame, the moments of inertia about each of the axes, those are fixed. That's the reason we assumed it. That's the reason we cast the dynamics in terms of that system. So the only thing we need to worry about taking the time derivative of in the body frame are the components of the angular velocity vector. And so we find that the time derivative of the angular momentum vector, as seen in the body frame, is just this. So we get lambda 1, omega 1 dot, lambda 2, omega 2 dot, and then lambda 3, omega 3 dots. And then next, let's bring it all together. And so remember, this is our overall dynamical equation, and all we've been doing so far is working out the different components of that. Let's look at just the first component here. So the first component, the time derivative of the first component of the angular momentum vector is lambda omega 1 dot, and that's going to be equal to the torque about the first principal axis minus lambda 3 minus lambda 2. So the difference between the moments of inertia for the other principal axes times omega 2, omega 3. And we get similar expressions for the other three components. I'll skip to the end and show those. Okay, so here are Euler's equations in all their glory. We can see some nice parallels with Newton's equations for dynamics. So here we see on the left-hand side, we have an inertia. So this is, in this case, this is a moment of inertia. In the case of Newton's equations, it would just be a mass times the time derivative of a velocity. So that's an acceleration. So in this case, we're talking about angular accelerations. On the right-hand side, we have what is the equivalent to the applied forces. So here, that's the applied torque to the system, the component of that torque about the first principal axis. And then we have this term over here, which involves the angular velocity components about the other two axes and the difference between moments of inertia. This term appears, remember, because we're in a non-inertial frame. We're in a rotating frame, which is rotating with the body with an angular velocity omega. Okay, so because we're in a non-inertial frame, we don't just get F equals ma, we get F equals ma plus the non-inertial term, and that's what these each represent, these terms at the end of the Euler equations. So in general, it's difficult to solve these equations for each of the omegas as a function of time, because there's a lot of nonlinear coupling you can see here. So usually what we do is we take a simplified approach. We consider cases where the different moments of inertia are equal, and so these differences drop out, or we assume that some of these angular velocity components are constant. Lots of ways of approaching different problems so that we can make the solution to the Euler equations tractable. But this is the Euler equation in their full glory. In the next section, 10.8, we look at how to solve Euler's equations in the case that these applied torques are 0. And we'll see, of course, that that simplifies the problem immensely.